Okay, hello again everyone. So in this video I'm going to be talking about convolution, which I thought was a really cool topic in these past few weeks of discussions. And like the last discussion on reduction of order, I just wrote another page and started another, but I didn't quite finish it, so I'm just going to stick with convolution. But we'll start off with a definition. So for two continuous integrable functions, fg, we denote by f asterisk g the integral from 0 to t of ft minus tau g of tau d tau. And when we write this, we say f and g are convolved, or f is convolved with g. And so there are various interesting properties of convolution one of which we saw and proved in the lectures, which was commutativity, and that says that f convolved with g is equal to g convolved with f. And I've also written three others. I'm sure there are many others, but these were the three that rung for me. So associativity basically says that f convolved with the convolution of two functions is equal to f convolved with the first and the entire convolved with the third. And distributivity says, as we would expect, f convolved with the sum of two functions is equal to the sum of convolution of f convolved with either. And we can also reverse this by commutativity and say that the sum of two functions convolved with f will also distribute from the right. So we also have scalar multiplication for a real or complex constant lambda times a convolution. We can associate lambda with either of the functions or put it on the other side and obtain the same result. Note that we cannot associate lambda with both of them. So it's not like addition. If it were lambda times f plus g, then we would distribute lambda through, but in this case it can only be associated with one or the other, or neither on the outside. And for the proof of associativity, I had a bit of trouble with this one, so I didn't quite finish in time for the due date of this discussion. But if you have any suggestions for how I might complete this proof, I believe I've written drawn up the region of integration correctly, although if you have any commentary or suggestions or critiques, feel free to let me know. I'll try to make the necessary changes to make this page better. And then for distributivity, this proof is pretty simple. So f convolved with the sum of two functions is equal to the integral from 0 to t of f of t minus tau times the sum of the two functions of tau, d tau. So tau is our dummy variable. I remember a few of you wanted an explanation for that earlier in the semester. So tau is just our dummy variable. It doesn't really matter what tau is. We can put in a Greek letter phi or tau or omega. It doesn't matter. As long as we realize it's the variable of integration, we're okay. It all means the same thing. And now we can distribute f through this sum and obtain this integrand. But by distributing the integral through, we can break this integrand up over addition and obtain two convolutions, f convolved with g and f convolved with h, the sum of those two. Now back here in the integrand, we could have reversed the product of these two functions, and then by substituting u equals t minus tau, as we did in the lectures, we could reverse the convolution and obtain the opposite result, as I wrote up here, so g plus h convolved with f. But another route we could take is by using the commutativity rule that we've already proved. We could just reverse f and g and f and h in this step, and then rewrite the integrals using definition 1, and then pull the f out of both sides to the right, and then we get the sum of the functions, and the sum of the functions convolved with f, because this integral is a convolution, and that completes that proof. This leads us into a rather interesting property of convolution integrals. So for many of the operators or transforms we have seen, like the Laplace transform, maybe even the Fourier transform. I know I wrote a post about that like a week ago or so. Or even the differential operators. So those are all examples of linear operators. They take in functions, constant multiples of sums of constant multiples of functions, and spit out the sum of constant multiples of transforms of the functions. Yeah. So they satisfy this property here, which I basically just verbally described, and the convolution integral, on the other hand, is even more than linear. It's bilinear, and we can see that by the distributivity rule, basically, and by a combination of the distributivity rule and scalar multiplication. So we recognize by distributivity that it is linear in both positions, either f in definition 1, f or g. In positions f or position g, it's linear, and it's also we can also pass a scalar multiple in because it's an integral. So and we can do that in either position. So it is a bilinear transform in a sense. I hope I'm not butchering the terms, by the way, but I believe transform is the right word. If not, again, just let me know if you now this can also be extended to multilinearity. So in text, this reference to in this book, Tensor Analysis on Manifolds by Bishop and Goldberg, we know that they have a more formal discussion about multilinear functions and spaces and dual spaces and all of that fun stuff, tensors. I can't wait to learn about it in future classes, but for now, I think these are the necessary conditions extended from the bilinear definition. Now we're going to utilize two more theorems in the 5 problems that follow that I decided to work out in this video. So theorem 1 is the Laplace transform of convolved functions. The Laplace transform of the convolution of f and g is equal to the product of the Laplace transform of either of f and g. So it's the Laplace transform of f times the Laplace transform of g, and this is a useful theorem that we're also going to use in one of the problems below. It basically says that the Laplace transform of t to the n times f of t is equal to this negative 1 to the n times the nth derivative with respect to s of the transform of f of t. So we'll use that below. Now I'm going to I've taken 5 problems from section 8.6 of the Trench textbook. Problem number 2, I did A through E, and we're going to work through the proofs of each of these results. So for the first one, it's the Laplace transform of this integral, and we recognize that this is the convolution of sine of at and cos of bt, because by definition 1, again, if f is sine of at and g is cos of at, then this would, or we can even reverse it by commutativity. We would obtain this convolution. And since we know by theorem 2 that, or sorry, rather theorem 1, that the Laplace transform of convolution is equal to the product of the Laplace transforms, as I've written in this step, we can take the Laplace transforms of either of both of the functions and then multiply them together. And the Laplace transform, as a quick review of sine of at, is a over s squared plus a squared, and cos is the opposite on top, same on the bottom, s over s squared plus b squared for b, and then we multiply them together as as over a squared plus s squared, and the entire thing squared. Now for this second problem, we utilized one further trick, I think. So by definition 1, we have a convolution integral of e to the t times sine of at, and then by theorem 1, again, the Laplace transform of a convolution. We have the Laplace transform of e to the t times the Laplace transform of sine of at, and the Laplace transform of e to the t is 1 over s minus 1 times, and the Laplace transform of sine of at, as in the former problem, is a over s squared plus a squared, and multiplying them together, we get a over s minus 1 times s squared plus a squared. I'm a big fan of hyperbolic trigonometric functions, so I liked this example. This was a really good example, actually, I think, because I broke it down to the exponential definitions, which might be a good review. So by definition 1, again, we see that this is a convolution, and the Laplace transform of convolution is the product of the Laplace transforms. And by definition, the hyperbolic sine of at is equal to e to the at minus e to the negative at over 2, and cos hyperbolic at is equal to e to the at plus e to the negative at over 2. So the only thing that changes between these definitions is a negative for the hyperbolic sine, and a positive for the hyperbolic cosine. Hence, the Laplace transform of hyperbolic sine of at. I always want to say it backward, sine hyperbolic, because the h follows the sine, but of s is equal to 1/2 the Laplace transform e to the at of s minus 1/2 Laplace transform of e to the negative at. Again, as I mentioned above, this is a perfect example of the Laplace transform being a linear operator. So it's a linear transform. It satisfies this definition, this axiom, rather. And the Laplace transform of e to the at is 1 over s minus a, and 1 over s plus a for an a of opposite parity. And since we multiply this by s plus a over s plus a, and this second fraction by s minus a over s minus a, it simplifies to 2a on the top over the product of the denominators s plus a times s minus a, and then the 2's cancel between the numerator and denominator, and we end up with our expected result of a over s squared minus a squared. And then for the second problem, the Laplace transform of e to the at plus e to the negative at over 2, we can split that up using the linearity of the Laplace transform, and it's the same thing, except we have a positive in between, and so we add these together, and we obtain an s on the top after the 2's cancel between the numerator and denominator, and obtaining a like base. So it's virtually the same thing, except we have an a on top of the sine, the hyperbolic sine, as with the regular sine, as we saw in examples A and B. So with the regular sine, we end up at an a over s squared plus a squared, and with the hyperbolic sine, we end up with an a over s squared minus a squared. Yeah. So the only thing that changes is the parity of in the denominator, and then we multiply these two Laplace transforms together, and we obtain this result, which matches what we have above. In the fourth example, this one we had to we rearranged the integrand a little bit. So at first sight, it's not exactly recognizable. It looks a little scary, but after we move this 1 minus tau over, actually this should be a t minus tau. I'll fix that. We move this t minus tau over next to the cosine of omega t minus tau, and then this is all one function, and this is all one function. So this might be our g, and this might be the t minus tau cos of omega t minus tau in definition 1 might be our f. I've just reversed it by commutativity. And again, the Laplace transform of a convolution is the product of the Laplace transforms, and I've just denoted each of these individually by I1 so we don't lose track of them. And then this is the problem that utilizes theorem 2, which is why I thought it would be a good review. And so I1 is equal to the Laplace transform of t sine of omega t, and that's equal to negative 1 to the first times the first derivative with respect to x of the Laplace transform of sine of omega t. And the Laplace transform, again, of sine of omega t is omega over s squared plus omega squared, and then we use a quotient rule to determine the derivative, and the negative negates the negative top times bottom, so we end up with a positive fraction 2 omega s over s squared plus omega squared, whole denominator squared. And then for the second, it's basically the same thing, except in the numerator we end up with an s squared minus omega squared, a few fewer things canceled in the numerator. And then we multiply these two Laplace transforms together, and we obtain the Laplace transform of the convolution. So I1, I2 is equal to, or the product of the Laplace transforms is equal to 2 omega s squared minus omega squared over s squared plus omega squared to the fourth. So a high degree denominator in that problem. And then for the last, there was an e to the t outside. So I'm thinking, so the first thing that goes off is, well, there's probably a there's probably a horizontal shift in the s domain, and sure enough, there's an s minus 1. So first off, the integral, for this integral, we can recognize this as a convolution, but by the the scalar multiplication property of convolution integrals, we can pull the e to the t into one or the other. So e to the t can come in with the sine of t, as in this step, or the cosine of t, or we can just put it to the other side. And so I tried to emphasize that with all of these steps. And I chose to stick it with the sine of t because it's always easier to take the Laplace transform of a sine instead of a cosine. I don't know why, it's just easier to remember. And then, so the product of the two Laplace transforms with the e to the t stuck with the sine of omega t, and the Laplace transform of e to the t times a function, I suppose I could have written this as a theorem, is equal to the function with, if we denote the Laplace transform of a function by f of s, we get a horizontal shift, f of s minus 1. So it shifts it to the right one in the s domain. And we see that in the results. So I've just substituted s minus 1 for s in the Laplace transform of sine of omega t. And the Laplace transform of cos of omega t is just what we'd expect, is just the usual Laplace transform. There's no horizontal shift. And then we just multiply these two together, s omega over the product of these two binomials. And I was going to talk about integral differential equations because that is so cool. I mean, who thought of mixing integrals and differentials in an equation, as if differentials aren't hard enough? So, there's a lot of really cool examples, but I won't worry about them in this conversation to save a little bit of time. And In the future, if you check back, maybe I'll add a few problems. But I wanted to get to a quick application. At this point, you can either stop the video because beyond this point, there's little review, I guess. It's more of an application of convolution integrals. I found a really good paper that I'll discuss a little bit about. And so in the lectures, Professor Seeberger mentioned that convolution was used in signal processing, and that little light, because I remembered that convolution is used in astronomical image reduction, or while comparing results between different astronomical image instruments. So if we have, say, the Hubble telescope and the twin Keck telescopes in Hawaii, and we want to combine data from between the two sources of a particular object in the sky, we would have to use convolution kernels in order to combine the images. I didn't know, I haven't written programs to show this directly as of yet, but if I do, I'll try to post them to this thread, wherever this video is posted. And this paper, so we're going to go take a look at this paper real quick, and I'll discuss a few things in this paper that I thought were interesting. It denotes an image, an astronomical image, as I sub j of xy, where j denotes a particular camera, so a camera that's associated with a specific instrument or telescope, and a coordinate xy on the image that the telescope has taken. So you can go take a look at this paper. The paper is called Common Resolution Convolution Kernels for Space and Ground-Based Telescopes, as I mentioned, and you'll recognize some of the mathematics. First and foremost, the convolution operator. They write it as a star here, but it's really, they really mean asterisk. It's same thing. So if S denotes a source in the sky, say a star, then the image obtained of that star is equal to the convolution of that star with a point spread function. So a PSF, a point spread function, which they denote as capital Greek psi, is basically like your instruments take on the night sky. I want to say, so in this image, for instance, I'll just use an example. These stars are point sources, so no telescope on Earth could possibly resolve these stars to the size of their actual disks, like the edge of the sun. But so these point sources have been convolved with a convolution, or with a point spread function. And the point spread function, there are a number of ways of fitting a point spread function. For instance, this is an image from the Sloan Digital Sky Survey, and I mentioned this in a discussion post. I think a few of you were interested in what I was doing there, so I thought I'd provide a quick example of what I've written. And so I'm going to fit a point spread function, a Gaussian point spread function, to this star. And I know it's at the edge of the field, but the parameters that you have to arrive at aren't so simple to get, so I'm just going to use what I have. And so for this star right here, we can fit an approximate Gaussian point spread function. And by running the program, so this is just basically iteratively arriving at an approximate point spread function of a Gaussian shape. So it's like a bump function. It's fitting it to the star and normalizing it. And we see that, so let me show you what I mean. So here is a Gaussian function. This won't be here when the page is finished, but so I call it G sub n of a parameter vector theta, which contains these parameters alpha, sigma sub kappa, and mu sub x sub gamma, and sigma sub x sub gamma is over here. So the sigmas Mu's, and alpha. They are in the parameter vector theta. So this first column is alpha. The second and third are mu sub x sub 1 and mu sub x sub 2, and we're going to get a graph really quick that shows the convergence of these variables. But the last two columns are sigma sub x sub 1 and sigma sub x sub 2. So these are the standard deviations along the x1 and x2 axes of the star profile, the discrete profile, and the second and third columns are the centroid of the star. So they're like an xy coordinate of the centroid of the star. This is minimizing the cost of fitting a surface, a Gaussian surface, a two-dimensional Gaussian surface to the discrete profile of the star. And this graph just shows the convergence of alpha. So it was initialized quite far off, and then it jumped up to just above 1.0, and then converged slowly back down as the sigmas converged. And we can close this and look at the other graphs as well. So here's the convergence of sigma of the standard deviations along x1 and x2, and so they were initialized a little high, but then dropped quite a bit down, and then eventually converged, or appear to have converged. We can think of the process as crawling along a five-dimensional surface to a five-dimensional minimum, in a sense. So if we have a five-dimensional manifold, we're crawling along to the optimal parameters on that surface. And here's the convergence of the centroid, so x1 and x2. So the centroid converges really fast also. The sigmas, the standard deviation, do not converge very fast. And here's the total cost, but that's associated with the algorithm. And so the parameters that we've arrived at with this quick iterative fit, this last column here, these five numbers, if we throw them into a two-dimensional Gaussian surface and plot it, as I've done on Professor Seeberger's applet, so here's the surface that we've fit with that algorithm. And if you're interested in the details of the algorithm, you can just send me an email or something, or maybe I'll even post the source code if you really want to take a look at it. But so here's the Gaussian surface that we fit to that star's profile. And we see that it is indeed Gaussian, and it's a minimized fit, approximate minimized fit. So what does this mean? So what is this point spread function used for? Well, as in this integral here, so we have, so for equation 3, if we take the image A of this source S and we convolve it with a kernel from the convolution kernel to go from image A to image B, taken through an instrument A to an instrument B, then we obtain the second image as if it were taken through the other telescope. And there's interesting properties that arise in the Fourier transform. So this basically says that the Fourier transform of a point spread function, or rather, of a point spread function of B is equal to the Fourier transform of the convolution of the point spread function of image A with the kernel from A to B. So if we have a convolution kernel from A to B, which we can solve for if we know the point spread functions from this algorithm or an even more efficient one, we can take the Fourier transform of an image with that kernel after we've solved for the kernel, and the Fourier transform of the convolution is equal to the product of the Fourier transforms. So the Fourier transform of a convolution has the same properties as a Laplace transform of a convolution. which is really interesting. And I'll post a link to this paper as well, and you can see the results. They're really quite fascinating. And that's about it.